Hello everyone, welcome you all at Lucas sir and I'm Test Zone. So today in the context of AC, we starting the LCR circuit response series resonance conditions. Before we have completed the relation for impedance, net impedance is given by Z equals to under root R square plus XL minus XC whole square. This is the relation for impedance, and tan phi angle of phase equals to XL minus XC upon R, and the resulting EMF, the alternating EMF in the RLC series circuit is given by E naught sine omega t plus 5. So these are the three relations so far we have derived. Now today we have the three cases here. Today we have the three cases. First, you check we have the relation for Z equals to we derived that Z equals to under root R square plus XL minus XC whole square. Okay. So there may be a condition that whenever XL equals to XC means capacitive reactance equals to reactance equals to inductive reactance. In that case, if XL equals to XC, this means they having the same value. So this term will cancel. XL minus XC becomes 0. Fine. So in that case, you have the minimum value of resistance because these two terms are frequency dependent. Okay, these two terms are frequency dependent. As these two terms are frequency dependent, but resistance is independent from the frequency. So at the time XL equals to XC, you will have the minimum value of impedance. It means the impedance equals to minimum. So it will be the minimum impedance equals to R square plus 0 square whenever XL equals to XC. So Z minimum, the minimum value of Z is equals to R. Okay. So for a series LCR circuit or RLC series circuit, yes, they will cancel the effect of each other. Okay, and this circuit will behave as a purely resistive circuit. Means in the case whenever XL equals to XC, so these two component will cancel the effect of each other, and the circuit having the minimum impedance, or you can say at that time the net impedance of the circuit becomes equals to R only. Okay, so the circuit equivalent is like a purely resistive circuit because they are not in used. Okay, so this is equals to R. Okay, minimum value of the impedance equals to R when XL equals to XC. So when XL equal to XC, then tan phi equal to 0. Now talking about tan phi, we have derived for the relation for the angle of phase, and we've seen the angle of phase for a RLC series circuit equals to XL minus XC upon R. Clear? In this situation, whenever XL equal to XC, the value at the numerator becomes 0 by R. So tan phi equals to 0 means phi equals to 0 degree. Means angle of phase equal to 0 degree means alternating EMF oblique voltage or current are in same phase. The phase of angle of phase delta phi or phi equal to 0 degree. Clear? Means current is in same phase with applied EMF. So check whenever XL equals to XC, then tan phi equal to 0. This means phi equals to 0 degree. Second case, there are two cases for Z, as the value of Z equals to R square plus XL minus XC whole square. In the phasor diagram you have seen there is the voltage for inductor VL equals to I into XL. As I is constant in the circuit, so here the utility of XL will define that VL will be more or VC will be more, XL or XC. Similarly, VC is 90 degree out of 90 degree lagging. Here the voltage for capacitor lagging behind the current by angle 90 degree. So VC equals to IXC. VC equals to I into XC. Clear? So the value of VC and VL actually depending on XL and XC. So whenever XL is greater than XC, whenever XL is greater than XC, it means IXL will be greater than IXC. Clear? So VL, inductive voltage, will be greater than the capacitive voltage. So that time the phasor will be break in the direction of VL, and the resulting voltage you will have VL minus VC. Fine? Because the VL will be the larger voltage. So the resulting voltage will be VL minus VC. Clear? So this time your circuit will be inductive dominated circuit. Okay. So when XL is greater than XC, then 10 phi will be positive. Yes, why 10 phi will be positive? Because the resulting voltage will be like this. Check here. This will be your parallelogram, and your resulting voltage will be like this. This is V, and your phase angle equal to positive. Yes, correct. It is in anti-clockwise. So anti-clockwise angle will be taken as positive. So here the phase angle phi will be positive. Hence voltage leads the current by in phase angle phi. Clear? You can see here that voltage is leading the current. Where is the current? Here it is. So it is leading the voltage. It is leading the current. The voltage is leading the current by an angle phi. On the other hand, if you see whenever XC is greater than XL, so IXC will be greater than IXL. Okay. So this will become VC is greater than VL. Okay. VC greater than VL. So yes, VC will be larger. So the this VC phasor of VC will be more. Now your breaking of voltage will be take place in the direction of VC because it having higher value. So your resulting voltage will be VC minus VL. Fine. Okay. So if you make the diagram, parallelogram, here it is VR. So your net voltage or net EMF is, you see, it is lagging behind your applied current. Clear or not? So it is phi in clockwise direction means there is a lagging of net voltage. So when XC is greater than XL or XL is less than XC, the 10 phi is negative. So angle of phase will be negative. Hence the voltage lag behind the current by an phase angle of phi. Clear? Yeah, note this. Okay, so mainly three situations are there, students. When your circuit is having both values are equal for XL and XC, then your circuit will be pure resistive. Yes, your circuit is said to be purely resistive. Purely resistive. Okay. When XL is greater than XC, your circuit will be inductance dominated. Okay. Here it is inductance dominated. So somewhat it is said to be inductive. And here your circuit will be capacitive. Not pure capacitive. Yeah, inductive dominated. Better to write the dominate. Here capacitor dominated circuit. Capacitive dominated. Clear? So three situations may be there. Okay, see student, three electrical circuits having AC sources of variable frequency are shown in the figures. Initially, the current is flowing in the each of the three is same. Means beta, they having the same current on initial stage. Say I. Okay. Same. If the frequency of the applied AC sources increase, then how will be the current flowing in these circuits will be affected? Give reason for your answer. Okay. So we have the three circuits. First is pure resistive. Second is pure inductive, and third is pure capacitive. Students, we know in the pure resistive circuit, your net resistance, or you can say if you say net impedance, so this is R, and R is independent from frequency, means it is not depending on frequency. So no matter how much you increase the frequency, okay, the current will be remains unchanged because it is independent from the frequency. Clear? Resistance will remain same. Clear? Here second, during the pure inductive circuit, your reactance becomes XL. The resistance here is appear as reactance, and the formula for reactance, see students, XL equals to omega L, and omega equals to 2 pi FL. Okay. So on increasing frequency, your XL will be increases because XL is proportional to frequency. So XL will be increases and your current become your current equals to I equals to I naught is equals to E naught upon XL. Clear? So increasing the value of XL, current will be decreases. So in the second case, your current will be decreases inversely proportional to the frequency. So for a inverse relationship, there will a graph of rectangular hyperbola. This is called rectangular hyperbola, or you can say Boyle's law graph. Maybe you studied the Boyle's law. P is inversely proportional to V in class 11th. This like graph was there. So same the flow will be here. If you're talking about the RMS current, so RMS current equals to VRMS upon XL. So VRMS upon 2 pi FL. So clear the here the DC equivalent or I is inversely proportional to the frequency. So with the increase in frequency of AC sources, inductive reactance increases as the current increases with the increase in frequency. Clear? Third part, the capacitive reactance decreases with the increase in frequency. Xc equals to 1 upon omega c. X equals to 1 upon omega c. So omega becomes 2 pi f. So it is equals to 2 pi fc xc. So if you increase the frequency, xc will be decreases. Okay. And IRMS becomes IRMS equals to applied ERMS or VRMS, applied voltage, Vrms upon Xc. So this is equals to Vrms divided by 1 upon omega c, or Vrms divided by 1 upon omega c means 1 upon 2 pi fc. This f comes to the numerator. So this is equals to Vrms multiplied by f into 2 pi c. Rest all the things are constant. It depends on frequency. So I is proportional to f. So there is a linear relationship between the I and F. So you will have a graph, straight graph, okay? A straight line graph. So this is equals to I is proportional to F. Clear? Yes. So this is the graph. So the capacitive reactance decreases with increase in frequency. So the current will be increases. Fine. Okay, next question is a resistor of 400 ohm, an inductor of 5 upon pi Henry, and a capacitor of 50 upon pi microfarad are connected in series across a source of alternating voltage. So you have an alternating source of voltage. Out of that, R, L, and C are connected. Fine. This is a series circuit with a voltage of 140 sine 100 pi t. So this is your voltage supply that is given 140 pi sine 140 sine 100 pi t voltage volt. Find the voltage RMS across the resistor. Means first you have to find VR, then find the inductor, then VL, and then capacitor VC. Okay. So you have to find the voltage, individual voltages across the resistor, inductor, and capacitor. Is the algebraic sum of those voltages more than the source voltage? You see here the source voltage, the maximum value of source voltage is given 140. Okay. So you have to check whether the sum of all the voltage is greater than the applied voltage. This is first thing. If yes, if your result is coming greater than the applied voltage, then solve this paradox. Why it is happening? Okay, done. Okay, so a resistor of 400 ohms. So we have first we have seen here that there is LCR circuit. So first you have to see the applied voltage. This is equals to 140 sine 100 pi t. Fine. Capacitive value, the capacitor, this is inductor, capacitor, this is inductor L. L equals to 5 upon pi Henry and resistance are given. Now comparing with the voltage V equal to V naught sine omega t. So the maximum voltage here, it is equals to 140 volt. Okay. So the maximum voltage this supply can provide, this is equals to 140 volt and omega is equals to 100 pi. On comparing with V naught sine omega t, so you see omega equals to 100 pi. Okay. Find the overall RMS value. So VRMS, equals to VRMS equals to V naught by root 2. Clear? So this is equals to V naught by root 2. V naught we have 140 upon root 2. So if you solve 140 divided by 1.4, okay, 1.41. So it is near about 100. No, 140 divided by 1.41. Let us solve it. 140 divided by sorry, 140 divided by 1.41. Okay, so it is about 100. Yes, guess is correct. Okay, it is about 100. Okay, omega is equals to 100 by fine. Now find inductive reactance. This is XL equals to 500 ohm. Capacitive reactance equals to this is okay, and impedance of the circuit equal to this much. Now find it the value of total current. IRMS equals to uh, IRMS equals to I naught by root 2. This is the value of total current. Okay, IRMS. VRMS across the resistance. So this is IRMS. Now you know in a series circuit same current will be flow. So the IRMS here equal to 0.2. Now multiply this IRMS and by R. So you will get the value of VR. So VR equal here equals to 80 volt, and VL is equals to 100 volt, and VC equals to 40 volt. Clear or not? So if you add them all, the total voltage VL, VR and VC will add up and will give you 220 volt. Yes or no? 40 plus 80 equals to 120. So it will be equals to 80 plus 180 plus 40. So it will be equals to 220 volt. Clear or not clear? But we have applied here a voltage of 100 volt. The RMS supply, VRMS, okay, calculated from the supply is only equal to how much beta? 100 volt. Yes. So input is 100 volt and output is equals to 220 volt. Is it possible? No, it is not possible. So why this coming? Okay, solve this paradox. Actually, we have avoided here. Okay, we have not considered here the phase relationship. Okay, so the VL and VC are in same phase. Sorry, VL and VC are 180-degree out of phase. VL is going upside and VL is going outside. VC going outside. Clear or not clear? Yeah. So VL and VC are not in the same phase. So the net voltage is given by the relationship VR square plus VL minus VC ka whole square. Clear? Yes, if this relation is valid only when both all of them, three of them are in same phase, then it can be applied. Actually, the net voltage can be calculated by the this relationship, that is utilize the phase relationship. Fine. Okay. Okay, student. Our next topic is electrical resonance. So everyone wants to know what is the phenomenon of resonance. The phenomenon of resonance is common among the system that have a tendency to oscillate at a particular frequency. This frequency is called a natural frequency of oscillation of the system. So student, there are uh, two frequencies. First, it is the oscillation frequency is called natural frequency of the oscillation. Okay, it is a natural frequency. So this word is important. This is natural frequency. To understood the meaning of resonance, everywhere resonance, not only for electrical purpose, you must know about the concept of natural frequency. The phenomenon of resonance is common among the systems. They have a tendency to oscillate at a particular frequency. So every system has its own frequency. This is called its natural frequency of oscillation of the system. If such a system is driven by an energy source whose frequency is equal to the natural frequency. Yes. So the another frequency is the source frequency. Okay. Another frequency is the source frequency. So if source frequency becomes the natural frequency, clear? The natural frequency. If the source frequency will become to natural frequency of the system, then the amplitude of the oscillations becomes large. Yes, the amplitude of oscillation becomes large, and this resonance is then this time resonance is said to be occur. Okay, we can say that their resonance is occurring. Clear? So the condition of matching of source frequency with the natural frequency, then that time it is called the condition of resonance. Done. So here we are interested to see the series resonance condition. So series resonance circuit. First you have to make the series resonance circuit. A circuit in which inductance L and capacitance C and R are connected in series, and a circuit admits maximum current means the circuit have a capability to current in maximum value. You know, whenever the current will be maximum by the formula I equals to V upon Z. Z should be minimum. Yes or no? And the minimum value of Z equals to R means the circuit should behave like a pure resistive circuit, and to behaving it's like a pure resistive circuit, it should have the criteria XL equals to XC means inductive reactance should be equal to the capacitive reactance. Fine. Then only you will have your impedance equals to R. So the circuit admits maximum current corresponding to a given frequency of an AC. Yes, corresponding to the given frequency of an AC is called series resonance circuit. So this circuit is called series resonance circuit. Yes. You know, if I making the graph for the XL and XC, check here the graph XL. The formula for XL equals to 2 XL equal to omega L. This is equals to 2 pi FL. Means resistance, capacitive reactance is directly proportional to frequency. So if you draw a graph starting from the zero frequency, when you have a given frequency, then this may be start from here. But I starting from the zero frequency, there will be a graph starting from zero. So this is the graph for XL and frequency, right? On the other hand, XC equals to 1 upon omega C equals to 1 upon 2 pi FC. Okay. So XC is inversely proportional to F. Inversely proportional to F means this is for XL, and another graph, if this is XL and say I make this XC versus frequency, here is also versus frequency. So on increasing the frequency, your XC will be decreases, and like this graph. So if I plot the graph on the same planes, XL and XC both, here XC represent the green line. So you check at a point here. By increasing the frequency, XL increases, and similar here XC decreases. So definitely there will be a some point whenever XL meet with XC. Yes or no? So there, this is the point of resonance, and this frequency is called resonating frequency. So at very low frequencies, inductive reactance XL equals to omega L is negligible, but capacitive reactance X equal to omega C is very high. So yes, you see the graph here. XC is very low. At start it is increasing. XL increasing, and XC is very high, so it is continuously decreasing. As the frequency of the alternating EMF applied to the circuit is increased, XL goes on increasing and XC goes on decreasing. Okay. At particular frequency of omega, yes, say it is equals to omega R. Okay, so at omega R, at the moment, say the frequency here is equals to angular frequency equals to omega R, and linear frequency will be FR. Okay. So omega R equals to 2 pi FR. This is linear frequency, this is angular frequency. So at the point, particular value of omega, say XL equals to XC, means omega RL equal to omega RC. Now, so omega R square equals to 1 upon LC. Now, squaring root, take the square root, so 1 upon under root LC. This is called resonating frequency, resonating angular frequency. Now, omega R will be equals to 2 pi FR. FR is equals to 2 pi 1 upon under root LC. Clear? So, this is called resonating frequency. We know at this frequency, XL and XC are equal. Check here the graph. The XL and XC will have the same value. So, at this value, your impedance equals to, by the formula Z equals to under root R square plus XL minus XC square. XL and XC both cancel each other, is they are equal, so it will give you R. Means Z having its minimum value. Okay. And you know I equals to V upon Z. So for a minimum value of Z, for a minimum value of impedance, you have a highest value of current, means the circuit will flow its maximum value. Here the impedance of the RLC circuit is minimum, and hence the current I not equals to E naught by Z, that is equals to E naught by R. So current in this situation becomes I equals to E naught by R, becomes maximum. This frequency is called the series resonance frequency. Clear? This is called series resonance frequency. Now check the graph of series resonance frequency. We have the formula I equals to E naught by R. Okay. Check here. This is the resonating frequency, and these are the surrounding frequency omega 1 and omega 2. Okay. At the case of resonating frequency, the current flowing equals to I equal to E naught by R. This equals to this is equals to I naught. Fine. Hmm. So the maximum value of current will be flown through the circuit. So check at the value of omega R. The current will be maximum. This is equals to I naught. Clear? This is equals to I naught, means 100% amount of current, maximum current. Now take the two places where current having its value as IRMS, means 0.707 or 70.7% of the peak current. So the two places here, yes, check here, this is equals to I naught by root 2. This is IRMS. Now if you cut this graph, then you have two positions of omega. This is omega 1 and omega 2. Clear or not clear? Yes. So the omega r will be at the center of your omega 1 and omega 2. Clear? And this band, the width of the band is called bandwidth. Yes. So this is called bandwidth. Okay. Delta omega. Delta omega is called bandwidth equals to omega 2 minus omega 1. Clear? Yeah, so these are the frequency. Corresponding frequency at I naught upon root 2. First frequency, the minimum frequency is omega 1. Then it is omega 2. And the difference between the two frequencies is called bandwidth. You see, student, that I equal to E naught by R. I equals to E naught upon R. I naught equals to E naught upon R. Clear? So if you increase the value of resistance, the value of I naught will be decreases. So here I am presenting two graphs here for a less resistance, and this is for a high resistance. So say this is the graph for R equals to 10 ohm. And if you increase the resistance, the graph will be decreases. See here, this is the graph for R equals to 100 ohm. Clear? So the value of maximum current will be decreases now for R equals to 100 ohm. Clear? Yes. So yes, write this first. Okay, so now see the observations. The variation, the variation in of circuit peak current with the changing frequency of applied voltage is shown in figure. First point, it is clear that for a frequency is greater than or less than omega r, the value of peak current or also less than the maximum value of current. Means if you have a value greater than omega r or less than omega r, you check at the value less than omega r, your current will be of less amount, and greater than omega r, your current having in less amount. Clear? Means at only omega r, your current will be maximum. Is selective frequency. So current, the peak current are less than the maximum value, that is I naught. At omega equals to omega r, the value of peak current is maximum. Yes, the value of peak current will be maximum at omega equals to omega r. Clear? Now, applications of this series resonance. Series resonance circuit is used in the radio and TV receiver set. You see, there is a frequency in a TV receiver set. There are a circuit is called tank circuit. So there is a LC circuit in every TV receivers and radio receivers. Fine. So this circuit having a frequency of 1 upon 2 pi under root LC. Clear? 1 upon 2 pi under root LC. This is a circuit of this circuit. Clear? Now, the antenna intercept a radio signal that also having its signal frequency. Clear or not clear? So when natural frequency of the circuit is equals to the source frequency, clear, signal frequency, then resonance will be occur. Clear? So if they both the frequencies are equal, then the circuit will have its maximum current. So series resonance circuit is used to in TV and radio receivers sets. The antenna of a radio or TV intercept the signal from many broadcasting station. Okay, like there is a antenna that receive the frequency. This is a radio set or TV set. It having antenna, and this antenna receive the signals from many TV channels or or radio channels. Fine. Yes. To receive one particular radio station TV channel, we tune our radio receiver set by changing the capacitance of a capacitor in the tuning circuit of the set, such as the resonance frequency of the circuit becomes equal to the frequency of the desired station. Like there in a this TV receiver or radio receiver, you have a circuit here. This is called tank circuit. Okay, and you have adjusted by varying the plate of capacitor, because the formula for frequency at any moment equals to 1 upon 2 pi under root LC. So with a particular value of capacitor, you have adjusted the frequency. Suppose it is 500 megahertz. Fine. So you adjusted your frequency of this circuit equals to 500 megahertz. Now this antenna will look that from which of the signal frequency is equals to 500 megahertz. If he match this antenna match the signal of the frequency 500 megahertz, then this circuit comes resonance with this signal, and resistance of the circuit will be minimum and current will be maximum. Clear? So circuit will come into the resonance of a capacitor in the tuning circuit of the set, such that the resonance frequency of the circuit becomes equal to the frequency of the desired station. Yes, frequency of the circuit becomes the frequency of the desired station. Therefore, the resonance occurs, and the amplitude of the current with the frequency of the signal from the desired station becomes maximum, and it is received on our set. Okay, and you will hear the broadcast, what is broadcasting there over your radio set, or you can tune your channel into the TV set. Fine. So this is the use of application of series resonance. Next question, next topic is Q factor of resonance circuit. What is Q factor? Q factor means quality factor. Quality factor. What is meaning the quality factor? You say in the resonance is like in the diagram here, you check the resonance. Yes. Maximum the sharpness of this curve. Okay. Maximum will be the sharpness of this curve. This so greater will be the resonance performing here. Yes or no? And for a better sharpness, this bandwidth should be very low, because greater will be the bands, lesser will be the sharpness. Here you see the bandwidth is more, like your this is your I naught IRMS. So here the bandwidth is omega will be placed like here, and omega 2 will be somewhat here. Yes or no? So here the bandwidth is more. So lesser will be the bandwidth, uh, lesser will be the bandwidth, maximum will be the resonance takes place. Fine. Clear? Okay. So the characteristics of a series resonant circuit is determined. The characteristic of a series resonant circuit is determined by the Q factor or quality factor of the circuit. It defines the sharpness of the tuning at resonance, means how sharp your curve is. If your curve is not sharp, then your signal is like dull. Okay. And if your curve is sharp, you have a perfect resonance. Fine. The Q factor of a series resonance circuit is defined as the ratio of the voltage developed across the inductance or capacitance at a resonance to the impressed voltage, which is equal to the voltage across R. Means, say, Q factor, quality factor is defined as Q equals to VL upon VR or VC by VR. Remember the formula? Quality factor is given by VL upon VR or VC upon VR. Okay. So write the formula. Q equals to voltage across the L or R divided by applied voltage, voltage across R. Oh, sorry, voltage across L or C divided by voltage across R. So Q becomes VL upon VR. Fine. Now VL equals to XL into I. So it is equals to XL equals to omega R, because we're talking this one on the place of resonating frequency. So this is equals to omega R into L into I upon resistance V R equals to R into I. I and I get cancelled. This is equals to omega R L upon R. Clear? Omega R into L upon R. Series resonating frequency omega R equal to 1 upon under root LC. So if you place here 1 upon under root LC in the place of omega R. So L upon R into 1 upon under root LC. This 1L with the root L will cancel and will give you 1 upon R under root L upon under root C. So under root L by C. Clear? Because L you can write root L into root L. So R and under root L under root C. So 1L get cancelled out and here it will be 1 upon R under root L by C. Fine. Now quality factor Q equals to, next equals to VC by VR. So VC equals to XC multiplied by I upon X or R into I. I and I get cancelled out. So here it equals to XC. X equals to 1 upon omega RC. At resonance condition 1 upon omega C. So omega RC. So into R. Here one R is there. So place the value of omega R equal to 1 upon under root LC. So you will again get Q equal to 1 upon R under root L by C. Fine. Okay, so see the observations related to the quality factor. As R increased, the quality factor of the circuit decreases. Also, the sharpness of the curve will be decreases. So you see here, as R increases, you see, for R increases, the sharpness of the curve here decreases. Fine. For high value of R, the sharpness of the curve will be decreases as the quality factor decreases. The value of Q usually vary from 10 to 100. Quality factor varies from 10 to 100. So this is remembering fact. The electronic circuit with a high Q values would respond to a very narrow range. Yes, obviously, the high Q factor means sharpness of the curve will be high. Okay. So here this one, the RMS part, you can say bandwidth will be less. Bandwidth will be less. Another formula for the Q factor is also Q factor equals to resonating frequency per unit bandwidth. Okay, write also this one. Resonating frequency per unit bandwidth. Okay. So formula is equals to resonating frequency per unit bandwidth. Q is equals to delta, omega R divided by delta omega. So lesser the bandwidth, higher the quality factor. Got it? Lesser will be the bandwidth, higher will be the quality factor. Yes. So the electronic circuit with a high Q values would respond to a very narrow range. Obviously, for a high Q value, your figure will be sharp enough. Okay, and there will be a very less bandwidth. So for a high Q values, would the circuit would respond for a very narrow range of frequencies, and sharper is the resonance. Fine. Okay, students. Now check this question. In a series LCR circuit with a voltage across an inductor and a capacitor and resistor are 30 volt and 60 volt. What is the phase difference between the applied voltage and the current in the circuit? So quite simple question, student. You see VL equals to 30 volt. The RMS value of the VL equals to 30 volt and VC equals to 30 volt. You know VL and VC are out of phase. So as both are equal, so they will cancel each other. VL equal to VC, and your net voltage V equals to along VR. Okay. So V equals to VR. Clear? Mhm. S is a series circuit. So XL equal to XC. As VL equal to VC means XL equals to XC, because VL equals to VL equals to I into XL, and VC equals to I into XC. So IXL becomes I into XC, XL equal to XC. So the condition of resonance taking place here. Okay. Now this condition, what is the phase of difference with applied voltage and the current? Obviously, phase difference equals to 0. Because in series circuit, your circuit will behave like a pure resistive circuit and phase difference will be 0. So there will be no phase difference between the applied voltage and current. Okay, so next uh, question. The figure shows a LCR circuit with a L equals to 10 Henry, S equals to 4 microfarad, and R equals to 60 ohm, connected to variable frequency 240 volt source. Calculate the angular frequency of the source which drives the circuit at resonance. Okay, first you have to find the angular frequency omega R. So that is equals to 1 upon under root LC. Second, the current at the resonating circuit. So first I naught equals to V naught upon R. Okay. Third, the RMS potential drop across the inductor at resonance. The RMS potential drop across the inductor at the resonance. So see here, first part of the question, resonating angular frequency is given by omega R equals to 1 upon under root LC. So it should be 50 radian per second. Got the same answer, beta? Okay, then current from the resonating circuit, resonating frequency, IRMS equal to VRMS upon Z, VRMS upon R. So here the VRMS 240 volt source, you have not given the sinusoidal voltage, it means this is the VRMS value. So VRMS upon R upon 60, so the current will be IRMS equal to 4 ampere. Now the value of potential drop across the inductor and capacitor. So XL equals to omega L at series resonance. XL equals to omega RL. Omega R equals to 50 into L equals to 10. So omega RL equal XL equals to 500 ohm. Now potential drop VRMS equals to IRMS into XL. So it will become 2000 volt. Fine. Okay, students. See this numerical. When a given when a given coil is connected to a 200 volt DC source, means this is VRMS. A 2 ampere current flows, and when a same coil is connected to 200 volt 50 hertz AC. Okay, here it is DC source, means frequency was 0. Okay, and when it is connected with a 50 hertz AC source, only 1 ampere current flows in the circuit. Explain why the current decreases in the latter case. Okay. Second, calculate the self-inductance of the coil. So during the DC source, XL becomes 2 pi FL, so XL becomes 0. So that time Z becomes equals to R. There is a RC RL circuit, okay? So Z equals to R as XL equal to 0. But when AC you have connected Z equals to under root RL R square plus XL square. So that will be greater than R, because XL have certain value in AC and I is inversely proportional to Z. Hence, in DC, more current flows than AC. Clear, beta? So this is first case. When you apply inductor with an AC, so it will have some value. Okay, so impedance will be more than the resistance. So the value of the current will be reduces. Second, calculate the self-inductance. So in DC circuit, R equals to V upon I, that is equals to 200 by 2 equals to 100 ohm. In AC circuit, Z equals to V upon I, that is equals to 200 upon 1 equals to 200 ohm. Okay. So during the AC circuit, you have the voltage equals to V equals to 200 ohm and current flowing equals to 1 ampere. As it is given here, the current flowing is 1 ampere. So the resistance or impedance will be equals to 200 ohm. Now the value of impedance is given by Z equals to under root R square plus XL square. So squaring both the side. R square plus XL square equals to Z square. So XL square equal to Z square minus R square. And this way you find your XL. Okay. So XL equals to 2 pi FL. F you have given 50 Hertz linear frequency. So L equals to 100 root 3 upon 2 pi F. Place the required value here and you will have your answer 0.55 Henry. See the next question, student. The graph shown here depict the variation of current IRMS angular frequency. So the graph is between IRMS and angular frequency, mean current or effective current versus angular frequency for the two different LCR circuit. First having given the high sharp resonance and second having some less. Observe the graph carefully. State the relation between L and C values of the two circuits when the current in the two circuits are maximum. So two cases are here. First is to sharpness, the maximum peak is lying here and second is lying here, and the maximum current here is equals to 1 ampere and here it is equals to 0.5 ampere. So state the two relation between L and C. So between L and C you have to find the relation, okay, when the current in the two circuits are maximum. So you have to make the two relations for the two such situations. Second, indicate the circuit for which power factor is high. So power factor should be introduced here. So what is power factor? Cos phi equals to R by Z. So this is your power factor, okay? Cos phi equals to R by Z. So introduce power factor is higher. Second, quality factor is larger. Give reason for the each case. Done. Do it. Okay, students. So see the solution. Since for resonant angular frequency omega r is same for both the graphs. Here see the angular frequency for resonating frequency for both the graphs are equal. So we can consider omega r1 equals to omega r2. So under root L1 C1 equals to under root L2 C2 or L1 upon L2 equal to L2 upon C2. So this may be the ratio. Second question, indicate the circuit for which power factor is higher. In the given graph, IM1 is greater and in the graph 2, current IM2. So IM1 is greater than IM2. This means the resistance for the first circuit will be lesser for the second circuit. Okay. So the current in the first circuit will be greater. That means R1 will be lesser and cos phi equals to R by Z. Clear? So as cos phi is proportional to R, so for a higher value of resistance, the higher value of the power factor will be there. So the second one having the higher value of resistance, second circuit. So the for the second diagram, higher power factor will be there as cos phi is proportional to R. Next, talking about quality factor, Q factor for the both graphs. So by the diagram, it is clear that quality factor for the first graph will be greater than the second one because it is sharper. So Q equals to 1 upon R under root L by C. We seen that L by C is constant, so only dependence only on R. So as R1 is lesser than R2, so quality factor for the first curve will be greater than the second curve. Clear? So quality factor for the graph 1 is higher for the higher than the graph 2. Done. Okay, an inductor of 200 millihenry, capacitor equals to 500 microfarad and a resistance equals to 10 ohm are connected in series with a 100 volt RMS voltage is given here. Variable frequency AC source, calculate the frequency at which the power factor of the circuit is unity. Power factor of circuit is unity means cos phi equals to R by Z. Power factor we seen cos phi power factor equals to R by Z. So whenever R upon Z becomes unity means 1, this means R equals to Z. So they ask about the condition of resonance. Whenever your resistance will be equal to impedance means at the condition of resonating frequency. So you have to find the condition means XL equal to XC. This will be the condition. So power factor become unity. Second, current amplitude at this frequency. Simply it is equals to V upon R because maximum current will be there. Quality factor by the formula 1 upon R under root L by C we can get. So first the power factor becomes unity means phi equal to 0. LCR circuit in the resonance. So omega naught equals to 1 upon under root LC. So this time frequency will be equals to 100 hertz. Okay, 100 per second means 100 hertz. Okay, or it is omega, so it is radian per second, 100 radian per second. Fine. If it is omega, then it will be in radian per second, not hertz. 100 radian per second. Second case, IRMS at this situation, VRMS upon Z, VRMS by R. The value of Z equals to R. So at resonance, Z becomes equals to R. So IRMS equals to 10 ampere. Okay. So maximum amplitude, maximum value of current, I naught equal to IRMS into root 2. Why? Because IRMS equals to I naught by root 2. So I naught becomes IRMS into root 2, so it is equals to 10 root 2. Quality factor is given by 1 upon R under root L by C.